this example, I have a fan blade with a mass of 0.3 kilograms and a radius of 0.4 meters. It also has a radius of gyration of 0.12 meters and is accelerated from rest by a motor, so a fan motor, that applies a constant torque of 0.06 Newton meters. My question is, what is the angular velocity of the fan 3 seconds after it has started from rest? And let's go ahead and assume negligible friction. If you know how to start this problem, jump in, pause at any time if you think you can get ahead of me, and I'm going to go ahead and solve this problem. And before I completely solve it, I'm going to sort of outline my solution here. In order to figure out my angular velocities, I'm going to have to do some kinematics, because I actually don't think I have enough information here with the tools that I already know to be able to figure out anything. So I think from the tools I have here, I can use some of the moments equals I alpha to figure out the angular acceleration, and then I can use kinematics to solve for my final angular velocity. In fact, I think I can use omega is omega naught plus alpha t, assuming I have a constant angular acceleration. And my started from rest, so this will be 0. And so I know my time, and if I can solve for my alpha using some of the moments equals I alpha, I think that should be good. My moment, a torque is another word for a moment, so that'll be my moment. And if there's no friction, there shouldn't be any other moments. And my mass moment of inertia now I need to solve for. And I'm given the radius of gyration, so immediately I'm thinking my mass moment of inertia is just mk squared. And I think that will get me everything I need to get to the solution. So I'm going to go ahead and use that path to get to my final angular velocity. So first up, calculating my mass moment of inertia using my radius of gyration. So that's mk squared. My mass is 0.3 kilograms. My radius of gyration is 0.12 meters. So my mass moment of inertia here is 0.00432 kilogram meters squared. All right, that's step 1. Step 2, now sum of the moments equals I alpha. And this problem didn't actually tell me which direction this torque is, but it really doesn't matter whether it's positive or negative. That'll just determine whether my final angular velocity is clockwise or counterclockwise. Since it didn't tell me, I'm assuming it doesn't really care. It doesn't matter. So I'm not really going to do this in a vector sense. I'm just going to do what I have. So my only moment is the torque. So that's the 0.06 Newton meters. My mass moment of inertia I just figured out is 0.00432 kilogram meters squared times alpha. And this gives me an alpha of 13.89. And now let's think about my units. One of these meters cancels out right off the bat, but then I'm left with these weird units. And I remember that a kilogram is, or a Newton, excuse me, is a kilogram meter per second squared. And I usually remember that because I know that a force is a mass times acceleration, so kilogram meter per second squared. And then my kilograms cancel out, this extra meter also cancels out, and I'm left with 1/second squared. And in rotation, I can add those radians to remind myself that it's rotation over second squared. So my alpha should be 13.89 radians per second squared. And now the last step, using my kinematic equation to figure out my final angular velocity. Omega is omega naught plus alpha t. My initial angular velocity is 0 because it says it starts from rest. Angular acceleration is 13.89 radians per second squared. And I'm curious about 3 seconds after it starts. So that gives me a final angular velocity of 41.7 radians per second. And that's my final answer.